We've seen that a binary search tree allows us to look up information quickly by getting that binary search-like behavior of splitting in half every time we make a choice. But what a binary search tree lacks for us so far is the ability to iterate through, where in an array or a linked list we could get the first item, the second item, the third, and so on. That's a little more complicated in a tree. Now, in a binary search tree, we do know the first and the last items in it. We know that the minimum value, if we were going in order of the keys, is the leftmost node. We step left to get to lower values, and when we can step left no longer, we have the minimum node. And likewise, the maximum, the last item we would visit if we were going in order, is the rightmost node. But from those nodes, where to go is a little uncertain to us so far. What we need is the ability to define a successor, which we have done before when we were doing the two-child deletion case, and we'll now have to do for iterators or for anything that wants to walk through our tree in order of the keys. So we need that successor idea that from the minimum, where's the next value? Where's the second lowest value and the third lowest value? Finding the successor from a node X in a binary search tree is not exactly trivial for us. If X has a right child, if there's a right subtree under that node, then we know those values to the right of it are values higher than X. We want the lowest one inside of that subtree. We want the value that comes right after X, that comes immediately after X. It's successor. So the successor will be the minimum node in its right subtree. It will be the leftmost node in that right subtree. That's not too difficult. What gets much more difficult is that if it has no right children, if we were dealing with a leaf node or it's an internal node that doesn't have a right subtree, then its successor is the first ancestor whose left child is X or is an ancestor of X. Basically, that means we need to look for something above X in the tree where X lived on the left of that node. Something above X where X was a value lower than that value. This is a little complicated to find if we're trying to locate it from a given node. The predecessor will follow a similar concept, but is the prior element to it. So traversing the entire tree is really not too hard to do recursively. Trees work very nicely in recursive settings. So we could write a print function that printed out the entire tree based on some root. We give it the root of the tree first, and then it will get called recursively on roots of subtrees underneath that overall root. So if the node that we were given as the root of a subtree is null, we return because this subtree is empty, there's nothing to it. If it is not null, if it has a left child, we print out recursively the entire subtree to the left of this node because those will be all of the values lower than this node. Those will make recursive calls and so on. Once that whole left subtree is done, then we print out this node's value. Then we recursively print out the entire right subtree of this node, getting all of the values that are higher than it. This is very helpful for, again, something like printing the entire tree at once. It is not so helpful for something like getting the third element in order from the tree. To do that will require a little more work. We can, by the way, switch these around to get a pre-order traversal or a post-order traversal, which are other ways to traverse through a binary tree. We will deal with those for later uses. If we want a non-recursive traversal that allows us to get single items, then we may need some extra support in that. We could put nodes onto a stack and keep track of which nodes have been processed and which ones haven't, and that would allow us to do some of this. We also could add more information into the tree. For example, some people will solve this problem by adding parent pointers to every single node in the tree. And then that allows you to do that, looking for ancestors and all of that. We may be able to do it with less than the need for a parent pointer for everyone, and without having to do the work of that logic of, is it an ancestor where X is to the left of that ancestor? That can be a little messy. So one way that we can do that is to use a threaded binary tree. Essentially, it allows these threads of the pointers for leaf nodes that would have been unused anyway to point back to interior nodes, to point toward where their successor should be or where their predecessor should be in the tree. So those pointers were completely unused otherwise. They would have just been null. So let's use them for something. The only piece is that we will have to mark whether the pointer we're using is a real child or is being used as one of these threads to point to a successor or to point to a predecessor. So we will talk about right-threaded trees and left-threaded trees. Right-threaded trees are where the right pointer of leaf nodes is going to point to the successor, and we would need a Boolean to indicate, is my right pointer being used to point to a successor or to a real child? And likewise, a left-threaded tree would use the lefts of leaves to point to predecessors. Some trees will be threaded both left and right, and we'll see an example of that. This tree here, in fact. We could do an in-order traversal of this threaded tree by starting out the same way we normally would. Go left until we cannot go left anymore. We get to the A, and that is the minimum value. But instead of having to dig back and figure out where a predecessor or an ancestor is that we should be using, we just use A's right pointer to point to B, its successor, the next node in terms of values. So no matter what, we'll be following a right pointer from any node that we're sitting at. From A, we would follow that right pointer and we would see the isSuccessor Boolean is true. So that leads us to B and tells us we're ready to use B and to process it, print it, return it, whatever we're doing. If it's an iterator, make it the value. Then we jump back to step 2 because we've finished with B, and if we have to proceed from B, we'll go to its right child. Its right child is a real right pointer, and therefore we will look at that real subtree there, and we will find the leftmost node in that subtree, the minimum in that subtree. So from D, we get the minimum of C in that subtree. And then from C, we'll follow its right pointer because we return to step 2. We walked to the leftmost node from D. That returned us to step 1. Then we follow to step 2, meaning we're going to follow a right pointer. That right pointer leads us to D. It is a successor pointer, so we process D. Then from D, we go to its real right child, E, but it has no subtree under it, so it is the leftmost node in that subtree, and therefore we process E. Then I move right to F, and I'm up at the root node, and I could process F's value because that was a successor pointer, and then I'm going to be handling F's right, which is this subtree with G. G is the leftmost node in that subtree, so I would process G. Then I would look at G's right, which is the real child I that has a leftmost item in its subtree, H. So H would be the next one processed. H would lead me back to finally process I. Now we have the question of how our code would know to stop. So there are 2 possible stopping criteria. In the case where we were looking at before, I had no right child. So we know that the right was null, and this was the rightmost value, the maximum value in our tree. So we could deal with those nulls. We have preferred typically not to deal with those nulls if we can, for example, like sentinels in a sentinel list. So we can add to our threaded tree a dummy node or a sort of sentinel that the maximum valued node points right to that dummy node, and the minimum value points left to that dummy node. So if we were walking backward through the tree, once we reached A, then we would be led to that dummy, that sentinel route, and we would know that we were done. To start on real data, we go from that sentinel route, that dummy route, and we go left, left, left until we are at something that has no real children. So it's perfectly reasonable still to know that we're done here, either by those nulls trailing off the end or by reaching that dummy node. And that allows us to traverse the tree using only left and right pointers from the nodes.